Let's discuss now an example of the application of power and the Poynting vector for electromagnetic waves. Let's suppose we have a source of electromagnetic waves, and we have a surface here, S, and on that surface we have a Poynting vector that's pointing radially outward in the same direction as n hat. We know that the power, and I'll write power because we've been using radiation pressure and momentum, on this surface is, on our surface, is equal to the Poynting vector dot n hat times dA. And suppose that our surface is a radius r, then if S is pointing radially away, so what we're describing is a radiation that's spherically symmetric, moving outwards, then this integral becomes very easy. It just becomes S times the area of the surface, which is S times 4 pi r squared, where S, let's write that as the magnitude of the Poynting vector. So for this example, we can conclude that the magnitude of the Poynting vector is related to the power of the source divided by this area, r squared. So that means that as you move further away from the source, and as r gets bigger, the magnitude of the Poynting vector decreases, where we're assuming that we have a fixed power source. Now, you can apply this to many examples. You could apply it to, say, as a model for power emitted from a light bulb, which is a 100-watt light bulb, say. Or you could look at an example of a star, where the power is what is the power of the star? And then you can compute the magnitude of the Poynting vector at any distance from the star.